in this section, I want to talk about half and quarter wave lines. This means that I want to cut the transmission line into half wavelength or quarter wavelength, and then analyze the properties of the lines. And I want to emphasize again, because of this standing wave pattern on this transmission line, so we'll expect that the properties of a transmission line will repeat every half wavelength. But now we want to look into this rigorously from the physical model. So suppose that you have a envelope function for V and L, which we derived previously. And from this the envelope function, the variation of the value versus distance is decided by this phase. And usually the reflection phase is decided by the impedance. But this phase, beta L, is a function of a position on this line. So you can immediately recognize that this is a periodic function because if 2 beta L is the integer multiple of 2 pi, because the complex exponential for this case will have a periodicity of 2 pi. And if you spell out this the beta equal to 2 pi over lambda, then you end up having the periodicity equal to 2 pi is equivalent to a section length of half wavelength on this transmission line. So for a half wavelength line like this, you have a low at the end of the transmission line, and then suppose we look into the line at the location which is the integer multiple of half wavelength. Then you set this length into this calculation, and then you can come up with beta L equal to integer multiple pi. So all the sign will just go away because sine n pi is equal to 0. So the your input impedance right here turned out to be just equal to the low impedance. And this point is that we have emphasized a few times already in my lectures. So if you look into the line at location of the integer multiple of half pi, basically the line appears to be invisible. Basically you get an impedance equal to the low impedance. And for quarter wave line, we look into the impedance at some position of quarter wave length. Specifically, we look into the impedance at location which has a distance from the low by r multiple of quarter wave length. So with this, you can calculate the beta L. Turn out that this value is going to be equal to m pi minus pi over 2. So if you put this into the impedance expression, then your cosine will go away because the cosine pi over 2 gives you 0. And so your input impedance at this location will give you this value, which is the square of the input characteristic impedance divided by the low impedance. So this is some value that you can use later for impedance matching. And because this characteristic impedance can be manufactured for your transmission line. So I'm going to give you one example which utilizes this property to cancel out the reflection of the signal from the transmission line. On this page, I want to show you how to use the quarter wavelength line to cancel out a signal reflection from a transmission line. Suppose that you have a transmission line and the reflection coefficient is given by this expression, and then we knew already that if I can match the characteristic impedance to the low impedance, then I don't have reflection. But sometimes we don't have such a luck, and the characteristic impedance does not match to the row impedance. Therefore, you have some reflection. And one way to remove the reflection is to cut the row impedance from this problematic line, and then try to insert it with a quarter wavelength transmission line. And from here on, I can calculate the impedance looking into this line at this quarter wavelength position. And the key to remove the reflection is to set the characteristic impedance of this line, this blue line, equal to the Zi value. Therefore, you don't have reflection. But previously, you already calculated the input impedance for the quarter wavelength line. So now you can write down this expression. And the first part is basically the impedance matching condition. And the second part is the input impedance for the quarter wavelength line. And if you equate these two relationships, then you can come up with the value which is the characteristic impedance of this line, given by this expression. So if you properly choose the characteristic impedance of this quarter wave line, then you can remove the reflection of this line. So this is one interesting and also quite important application for a quarter wave transmission line. So in this session, I talk about a half wavelength line transform the low impedance into itself because you have the standing wave on the line with a periodicity of half wavelength. And we also calculated the quarter wave line impedance, which is given by this expression. And in this expression, we have the freedom to choose this characteristic impedance of this quarter wave line so that we can do impedance matching to remove the reflection from a line which was originally not matched. And so the value of the impedance, characteristic impedance you want to choose is equal to the characteristic impedance of the old line with multiplying with the low impedance and take square root of it. So this is the way you can do impedance matching and remove the reflection of signal from transmission line. Thank you.